hold on. Okay, sorry about this. I'm not completely happy with my screen. Okay, good. So, okay, let's start by going through the problems here. And if there are complaints, I would like to have us talk them through now, as opposed to you guys trying to hound anything else. Okay, so what is the first problem? The first problem states that you're given a string, okay, that strings that are on square brackets and curly brackets. And you have to decide, is there a way of, of nesting these things, okay? Are these things well-formed, meaning, okay, that basically it corresponds to a legal parenthesization. Every left thing has a right thing, and they are properly nested, okay? So what is the algorithm that I would be using? Okay, the algorithm that comes to mind has to do with using a stack, okay? And that what am I going to do? When I get a left parenthesis, I'm going to push it. When I get a left parenthesis, I'm going to push it. When I get a right parenthesis, I'm going to have to make sure that I have a matching left parenthesis for it. So I'm going to go pop and test. Does this match the same as that? Okay, if my left parenthesis is what you call it, if my left parenthesis is different of the different type, they don't match. Okay. Now again, I'm going to go check. I'm going to now have a right parenthesis. I'm going to do a pop and compare with what is already there. Okay. If I go through and do it this way, there should be a for I goes from 1 to n, do a constant amount of logic of pushes or pops in there, okay? And based on that, it should be something that is order n and using a stack. And you have to check your logic conditions carefully enough to make sure it does this. Some people may vaguely say they have a stack. Some people may vaguely say they're going from left to right. Some people may not produce properly nested things. Any questions? There's some question of how much partial credit do you get if the algorithm is something like that? The answer is you get what the TA gave you. That is the important principle, okay? There will be, I think, an answer key given up, but it is uninteresting. If the TA looked at your algorithm and said that they think it's not quite as good as this thing, they gave you an extra point or they took off an extra point. This is uninteresting, okay? Any questions about this? So this should then be a linear time algorithm, okay? And it makes sense if you use the stack. Any questions? Okay, the second problem, maybe I'll change my pen color just for the sake of that, is the one that I thought was kind of the most interesting one here. Has to do with the H index, okay? It says that you're given an array of, of citation counts. Here I did this. And each paper has a citation count. And you want to figure out someone's H index. What is the number of papers they have published, that the maximum number of papers that have at least as many citations as that number? Okay, and this is a standard metric. The most simple algorithm to do this would be to sort the, the citation counts, which is 1, 3, 4, 5, 6. Actually, it's probably better to do it in reverse order. So maybe I'm going to go do it like that. 6, 5, 4, 3, 2. And I pair it up, at least implicitly, with the indices 1, 2, 3, 4, 5. Okay. And I look, what is the largest I? This is I, these are the counts. What is the largest I? Such that that the citation counts are greater than or equal to I. This tells me that I've got an H index of 3. So there is one algorithm here that runs in order n log n time, basically sorting and doing a linear sweep through this. Does everybody kind of see that? So one algorithm is n log n. Is that correct? Yes. Is that efficient? Well, you can do it more efficiently. Okay. Let's look at some arguments as to how you might do this better or more efficiently. There's two approaches to this that are better. One idea is based on median finding. Okay, remember that we talked about that. I guess what you probably had a homework. Okay, if I remember correct, on finding an expected time median algorithm. Does everybody kind of remember that? Does this sound right? People nod or tell me, or am I talking nonsense?
Yep.
Is that true?
Yes.
Okay. Now there is a worst case algorithm for finding the median in linear time. What would be the idea if we want to use this idea? Well, what if I find the median and use that as a, a partition, a pivot element in quicksort? Does everybody agree that the median is going to sit in the n over second spot? And after I partition it, all of these guys are less than the median. All of these guys are greater than the median. Does everybody kind of see that? Now I ask myself, is the median greater than, or how does the median compare to, is it greater than or equal to n over 2? Okay, the position of it is. If the value in the median element is greater than is greater than what is the second element, it's got to lie on that side. Does everybody kind of see that? If the median element, okay, is the number of citations is greater than n over 2, then the partition, but the split between where the h-index happens has to lie on the right. If not, it lies on the left. Okay? And then once I know that, I'm then interested, I can then try to find the median on the appropriate side. Okay? And by doing a logarithmic number of such median attempts, each of which is half the size of the previous one, my total time is going to be n plus n over 2 plus n over 2 plus n over 4 plus n over 8 ... which is theta of n. Okay? So does everybody see that if you can do linear median finding in linear time, this would give you that algorithm? Okay? Any questions about that? This is kind of clever. There's another way of doing it also, but I want you to, any discussions of this? Another way to do it in linear time would be to note that if none of the, if let's say the biggest number of citations, okay, what if, let's say, if we look at this thing, suppose we have one of your papers has a citation of much, much greater than n, okay? Then it doesn't matter any citation count that is bigger than the number of papers that you've read, okay? Written, okay? Does everybody agree that if all your numbers of citations were between 1 and n, that would be fine for doing the analysis? So what do I want to do? I am going to go through all the papers, and if you have a citation count which is greater than n, I'm going to replace it by n. So if I have a citation with 1,000,000 counts, but I've only published 1,000 papers, I'm going to replace it by 1,000. Now I've got an array where all the numbers are between 1 and n for citation counts. What if I now bucket sort this? Okay, if all my numbers are between 1 and n, okay, and they're integers, I can count how many papers are there with exactly I citations from 1 to n. And of course, anything that had more than n got counted up here. Now, after going through that counting, okay, I can go walk to the left and ask myself, do I have at least all of these papers have citations of at least n? My H index has to be that total, okay? And keep counting down until I get to the point where the accumulated number of papers with greater than I citations, okay? The moment we get to that point that is greater than I or less than I, that's the transition. So my claim is once I do a bucket sort of counts, I can walk from right to left and compute the I index in time basically proportional to my size of counts. I can set this up by having an array of size n, okay? I can do the bucket sorting in order n time, and then do the counting in order n time to try to find what this thing is. That's an alternate O of n algorithm. Any questions? Do people sort of see how that works? Any comments or questions? So for full problem on this, obviously you need a linear time algorithm, okay, to get full credit. Any questions? Any comments? Okay, any other clever solutions that people found? Okay, any way implementing this using a binary search tree? Well, let's think what a binary search tree should be. One is, it could be something like, you could use a binary search tree to do the sorting. That, of course, would be n log n, and that's probably basically true. Okay? With anything you do with a binary search tree, I think what you're talking about is binary search. Okay? Now, that gets to the second part of the problem. What if I give you the thing already sorted? Could you find the H index? And if you remember back to my first linear solution, once the thing was, remember my linear solution, it involved doing a binary search, right? Once the array was sorted, I was looking at the middle element and asking, is it greater than or equal to? Is the ith element greater than or equal to I? If I had the thing sorted, I could then do a binary search to find where was the transition between where the ith paper has, basically between it where it does and does not have at least I citations. So for the second part, actually, if I had the thing already sorted in log n time, I can find what the H index is. Do people kind of see what I'm doing there? If the paper was if it was perfectly sorted, if I look at the n over second position and I look what the value is here, if m is greater than n over 2, if these are sorted from big to small, if m is greater than n over 2, the H index has to be defined over there. If it is less than it, okay, then it's going to have to be defined over here. And that's a binary search kind of an argument, not a binary search tree, but a binary search argument. That if I had the thing sorted, I could do the search in log n time. Any questions about that? Do people kind of understand these solutions? So if it's sorted, log n will suffice. Okay. If it is not sorted, it would be order n will suffice. If you have an n log n algorithm, it does not make you a bad person, but it does mean you didn't come up with a maximally efficient algorithm. Any questions? Any questions about where we came from on that? Okay, the final problem has to do with finding anagrams, okay? And we said that we had two words, okay? Like, you know, let's take a look at silent and listen. And listen. How can we convert them? How can we tell whether or not they have the same set of letters?
You can sort the two strings and then compare them to see if they're the same string.
Okay, so one idea is, that's a perfectly reasonable idea, is to sort the letters in the thing, E, I, L, N, S, T. And here when I sort them, E, I, L, N, S, T. And now once you have them sorted, you would go and do a linear test for them. So one way to do this would be to spend n log n time, sort the two strings, and then do a comparison in linear time. Okay? Now, is that the most efficient way to do it? Well, one thing to note here is that, in fact, this says 26 letters. Okay? The strings have an alphabet that is of constant size. What if instead I did a counting sort kind of thing? I had an array indexed from A to Z, okay? And I ask you, I basically keep count. I initialize it to all zeros. And then I read through these things and increment the counts. I could build a table with the counts of the vectors, okay? And then I compare these two things. Now it takes order n time to get a representation of each string and to compare them. So in fact, you can get away with You can get away with doing this in order n time. That was the right answer here. Okay, you would have gotten partial credit for the general sorting thing, but the 26-letter alphabet was kind of the thing that you needed to see power. Some people wrote nested loops, said, well, for I goes from 1 to n, for I goes to 1 to n, check to make sure all possibilities. Okay. Bit vectors, again, bit vectors won't work because of duplicate letters. Okay. Some quadratic algorithms where you try to compare every character in one string to the other string will founder on duplicate letters. Okay. So that is what I was looking for here. Any questions about that?
I have a question how this two scores for each part relate to a score out of 100. What's the scaling on that?
So what I did was that the written part counts the same as the multiple choice part. And so we have taken your multiple choice number and multiplied it by 5/3 and then added it to your written part. Perhaps with added it to the written part. Okay. Okay, any other questions? So if you have the right answer, okay, that you had something where I have an algorithm that realizes the optimal time bounds, and they just didn't understand it, okay, then send mail to the TA men explaining why you have the right answer to one of these problems, okay, and we will look at it. But if we find, if there's something like, well, I kind of think I deserve more points, you may come back with less points, because I'm not in, I will be unhappy if she gives any points back on these kind of papers. And I have told her so. Okay? So the right thing to do is to, you understand, hopefully, where I came from on these answers. Okay? If there are any questions about it, I'd like the questions to be now. Any questions on the midterm, where we came from on this? Okay,
Yes,
and so on.
Professor.
Yes.
Can you explain where the m is greater than n/2 comparison one more time? I didn't quite get it the first time.
Okay, so let's take a look at this thing. Suppose, let's say, you want to know, again, we've got somebody here who has a, their H index, their you know, citations are sorted from biggest 200, 173, you know, 56. Okay, and in this slot over here, these are now sorted from biggest to smallest. What do I know if, when I have them sorted from biggest to smallest, the element in the n/2 position, suppose the element in the n/2 position here is if m is less than n/2. Okay, that's the element that we're looking at in the n/2 position. If so, the H index boundary has got to be on this side of the racket, right? If my n/2 paper, okay, has, actually, wait, let me just make sure I'm doing this right. If my n/2 paper has less than n/2 citations, my H index is going to be less than n/2. And that means the boundary has got to be somewhere on this side. And I can recur. If m is greater than n/2, or greater than or equal to n/2, it's got to lie on this side. Okay? And again, now I've got a problem half as big. Okay? And in a problem half as big, I'm going to look at the middle element here, in this case, the n/3/4 element, and ask myself, is the H index bigger or less than 3/4? Okay? If it is less than 3/4, if it's bigger than n/2 and less than n/3/4, it's going to lie on this part. So in a logarithmic number of comparisons, by doing binary search, I can find the right place. Any questions about that?
When you say m, do you mean the value or the index?
The value, n/2 is the index, right? There were a total of n papers written. M is, in this case, the value that is in the n/2 position. Right?
Okay.
The number of citations of my n/2 biggest paper.
Okay, so what if we have all the same value in the array? I'm confused on how m tells us the position
Well, because
in the
this
array.
is sorted, let's say let's say that I am publishing, let's say that, you know, I have written n papers, and each of these have received 2n citations. My H index is n. Okay, the criteria that you're saying here is, have I had it published at least this many papers with at least this many citations? If I have the papers sorted from most citations to least citations, then when I look at the median number of citations, either my median number of citations is bigger than n/2, or it is less than n/2. Okay? And if it is bigger, if it is less than n/2, then I know that my H index boundary has to lie on the left. It has to be less than n/2. if it's greater than or equal to it, then it's got to be from me to the right side. And in one comparison, I have halved the size of the array. How many times do I halve the size of the array until I get it from n down to 1? The answer is log n. Does that explain it? Or there's still mystery?
I think I got it. I think if I think about it for like a minute more, it'll make sense. Thank you.
Okay, then that's a well-spent minute. Okay, any other questions?
Yes, so would the overall complexity of this algorithm still be n log n because you're assuming that it's sorted from largest to smallest? Or rather, you have to sort it first from largest to smallest.
Okay, so we need the things sorted from largest to smallest. If we look at what the problem stated, as I recall, the bottom part, there were 2 written blurbs you had to fill in. The second one said, what if it was sorted? If it was sorted, you could then spend log n time and be done. That's what this is showing. If it was not sorted, you could sort it in n log n, and then do this, and then it would be n log n plus log n, which is n log n. Or you could do a linear, an easier part for the second phase, where you were just sweeping along and explicitly testing if the ith value is bigger than I. Okay? So in order to do if the thing is sorted, you can get away in log n time. If it's not sorted, okay, in fact, by one of the 2 clever ways, you can get away in order n time. But if not, you can get away at n log n time and get the correct answer and get a partial credit.
All right, thank
you. Any questions about that? Any other questions about the exam? Okay, so so this is what the results were, and like I say, don't worry about your absolute number. Worry about and don't really worry about your where you are relative to the median, which was a 68-ish. Okay, and the only ones that I'm really worried about, where I am concerned about whether I will be able to give them a good enough passing grade at the end, at this moment, would be the people in the 30s and 40s. So if you got in the 30s and 40s, you have to rethink what you're doing, okay? Possibly spend more time. Again, we have recitation sections. We have, we have a lot of TA office hours. I recommend working hard on the homework problems. Quite likely, if you didn't do well on the written part, that may be a function of not devoting enough time to the homework problems. Okay, but I encourage if you're in that category, those are the ones I'm worried about. By definition, that means I'm not really worried about the other people. Again, if you want to get a better grade than what you're currently averaging, figure out how to do better for the next midterm. Any questions?
I had a question. So does a certain like grade interval, like 60 or 70, 70, 80, something like that, does that have any correspondence with a letter grade?
No, I'm going to go and average all your final and your midterms and your homeworks according to the formula. I will sort them, and I know what my median is going to be, and I am going to divide that into reasonable bins, and I'm going to assign grades. Okay, so your goal is not to worry about this because it's my business to assign the grades. Your goal is to try to figure out how to get better on the midterms. Okay? Any questions? Okay, fair enough. Okay, if that's said, then I want to move on to the topic of today's lecture. Is that fair? Going once, twice, sold. Okay, so what I would like to talk about today, again, the material in the previous part, I know you've all seen to some extent, in your data structures class. What I would like to, oh, sorry about that. I suddenly realized you want to see my screen. You're not seeing my screen, are you? What do you, actually, yes, you are. You're seeing my lecture slide. Is that correct?
Yeah, it looks good.
Okay, good. Sorry about that. This is a little disorienting for me for various reasons. Okay, so let's talk about graphs. Graphs are one of the kind of really important ideas in computer science and important ideas in designing algorithms. A huge number of problems that people encounter in your computing life turn out to have a natural formulation in terms of graphs or networks. And there's a certain number of graph algorithms that are famous that everyone needs to know what's going on. And so being able to tell that your problem is a graph problem and knowing enough about graph algorithms to know what things about graphs are there good ways to compute is a way of solving a tremendous number of problems in real life. So, so I trust most of you have had some exposure to graph theory, perhaps in 215. Not necessarily so much. We'll talk here about what graphs are and it's important to kind of understand the concept and where they arise and stuff like that. A graph, as far as I'm talking about it, I'm not talking about an XY plot with jiggly line. A graph is a network. It's a set of vertices named V and a set of edges E, okay, where each edge consists of a pair of vertices, okay, and that edge can either be an ordered pair or not. So if we have a graph here, where we've got vertices 1, 2, 3, and 4, 1, 3 is an edge, okay? If it could be a directed edge, okay, meaning the edge goes from 1 to 3, in which case I'll call it a directed edge. If it's a directed edge, it is an ordered pair. If it's just a pair, then I guess it doesn't really matter. It's an unordered pair. But networks and graphs are very ubiquitous problems. There's a lot of situations in the world where networks occur, okay? Can anybody think of applications? Has anybody ever stumbled across a network in real life? What in the world is a graph?
Instagram.
Instagram, a social network.
I was going to say Instagram because...
Instagram, I'm assuming, is a social network. It means that what are the vertices and what are the edges? The vertices for
a follower.
Instagram. What you
A
have
vertice is a person.
The vertices are a person and an edge, IJ. What does that mean?
And an edge could be whether you follow them.
That means
whether you follow the person or the person follows you back.
Right. So again, I don't know. Is Instagram a directed thing? Okay. Maybe it's a directed.
Yeah, it's directed.
It's directed. Well, we haven't talked about what directed means. Meaning, can I follow you, but you not follow me?
Yes.
In that case, it's a directed graph. You're right. Any other than social networks, what other kind of graphs have people found?
If you were to represent like a bunch of cities on a map or something like that.
Okay, so this is my picture here. A lot of things that are road networks, okay? Typically in a road network, the vertices are cities or they are road junctions, and there would be an edge between any two vertices, okay? If there was a direct roadway between them, okay? And so in this case, whenever you have a network of roads, okay, you can drive from one place to another if there is a path of roads that follow it. So certainly, the road network is the system of roads and highways is a network. I've heard people talk about airports and airplanes. Yes, if every airport was of node and there was an edge between any two places where you could fly between directly, that would be a network, okay? And there's all kinds of natural questions that you can ask on these kind of networks. What is the best way to get from point A to point B? Okay, what is the shortest way to drive from Orient Point to Montauk? Okay, it isn't going to be like that, okay? And we will talk about shortest path algorithms. That's not right. Okay, we will talk about shortest path algorithms that find the shortest way to drive given the network. Okay. Another network that you know, is often useful to think about as a network is a electric circuit. This is a simple electric circuit where I guess you've got resistors in blue and capacitors in with the red bar. What are the vertices of this network, and what are the what are the edges? There are a couple of different ways to look at this circuit and see a network. Okay. What would be a way to do it? One way, I guess, would be to say that every junction between things is a network, and this would is a vertex. And so I've got 4 vertices: V1, V2, V3, V4, and then there are edges between certain pairs of vertices, and each edge represents a component, an electrical component. Does everybody see that? This could be thought of as a 4-vertex graph network. Well, graph, I like graph, okay? So I don't mean this, but I call them graphs, okay? Is there another graph that we could think of? Another way to look at circuits might very well be, we have a vertex represent each component. And we have an edge between any 2 components that are directly connected to each other. These 2 are connected to each other. These 2 are actually connected to each other 2 different ways. This one is connected to this, and I guess you could say this one's also connected to that. Does everybody kind of see what I'm doing here? This one is connected to that. This one's connected to that. Okay? So there are often different networks that you can define on the same data. And sometimes it's more useful to view it one way than another way. Any other networks people deal with that that they can think of, that they deal with on a regular basis or have encountered? Anyone else have a favorite graph? The internet. What are in the internet? What is the internet? The internet is, every computer on the internet is presumably a vertex. And there is an edge between me and another computer if there is a direct connection. That's one network associated with the network. What about the World Wide Web? The World Wide Web, I've got vertices for every web page and a link from one web page to another one if it has a hyperlink to it. So they're all, when you look hard enough, there are a lot of different, you encounter a large number of networks, and a lot of data that is, you know, problems that you would care about are naturally represented as networks. Any questions about that? Any other beloved network? Okay, what other ones did I talk about? I talked about a couple of these. We talked about social networks, the World Wide Web. When you write a computer program, certainly the people who compilers that translate programs from one language to machine language, there are a lot of graph algorithms in there. Why? You can kind of view a program as being a world where there are possible places that you jump to Okay, that you have a program can be written as a set of statements, and normally you flow from one statement to the next statement. But if this was an if statement, maybe if depending upon what would happen, maybe it would jump over to there. Maybe here I have a return statement and I can't go anywhere. Here I have a dead piece of code you can't reach to at all. Okay? I claim a lot of problems can be viewed as you treat each line of code as a vertex. Where can you flow to next? Okay, you get a control flow structure. It tells you a lot about your program. Any questions? Okay, so networks are a big deal. And if we can recognize that our problems are network problems or graph problems, okay, we are lucky indeed, because there are a variety of algorithms and techniques for dealing with this kind of thing. Any questions? Okay. So when I'm dealing with a graph problem, okay, the first thing that I do is I figure out what kind of graph am I talking about. One thing when you take a course in graph theory is you learn a lot of language, a lot of buzzwords, vocabulary, okay? Learning the talk, what does it mean for a graph to be connected, to be directed, to be weighted, to be acyclic, okay? These are important because once you know, this gives you a language to talk about your networks. And once you know about your network, sometimes what problem it is falls out naturally depending upon what kind of algorithm you have. What algorithm you should do will fall out naturally once you know what kind of network you have. Okay, so what I'd like to now do is talk about some of the main categorizations of graphs. And it's important you understand these words because, and what the implications of them are, okay? Because I'm going to use this vocabulary a lot. The first is the difference between directed and undirected graphs. A graph is undirected if edge xy implies yx is in the graph, okay? A graph is directed if that's not true. If there exists some kind of a pair of vertices where xy is an edge, but not yx, okay? Now, if we look at road networks that go between cities is almost always an undirected graph. If there is a road from one city to another, it almost certainly goes both ways. Okay, that if you drive to the city that way, you can drive home legally. On the other hand, within cities, it's fairly common to have directed edges, basically one-way streets. In a one-way street, you can get from one point to another, okay? But you can't necessarily get, you can't get back along that way. So the first question about you have to know about your problem is, do you have a directed or undirected graph? Any questions about that? Okay. In Facebook, the friends thing, is that a directed or an undirected graph?
I mean, it sort of depends, doesn't it? Because like, just because you can request someone to be your friend, they have to accept it as well.
Well, the edge, okay, so you're saying if I want to be your friend and you say no, well, the edge never exists.
Okay. So
I think that by the time the edge exists, if I am your friend, you're my friend.
So then, yeah, undirected.
Okay? Is Twitter a directed graph or an undirected graph?
Directed.
Twitter is directed. You guys can follow me, and I encourage it, but I'm probably not going to follow you, right? Okay? So you know, in general, X can follow Y without Y necessarily following X. Okay, and that's perfectly fair. Any questions? Okay, that should be clear. Many graphs are weighted. Okay, another question is whether a graph is weighted or not. In a weighted graph, the edge is associated with a numerical value. Typically, sometimes vertices are associated with numerical values, but usually it turns out to be edges. Okay? Is the road network a weighted graph or an unweighted graph?
Weighted.
Well, there are a lot of, it could naturally be weighted. What do the weights on a road network mean?
The speed limit or the length of the road.
Could be the speed limit. It could be the length of the road. It could be the travel time. It could also be, if you like scenic drives, you could have a number that represents how beautiful the road is. Okay? And maybe, you know, you might want to try to, that might be useful if you're trying to find the most scenic drive between two places. Okay? Does everybody agree that in a weighted graph, you have a number on each edge, and there's many natural, and like I said, for a typical network, there's often natural weights. Okay? In an unweighted graph, there is no cost distinction between the edges. Okay? It could be you think of an unweighted graph as a weighted graph where every edge has weight 1. Okay? Any questions? Certain problems we're going to care about. Is Facebook a weighted graph or an unweighted graph?
I mean, the type of relation is the same, so I think it would be unweighted.
I think as it is normally given, any friendship in a Facebook is an unweighted friendship, right? It just says that you and I are friends. They don't have a number measuring how intense this friendship is, right? Okay, now that might have been a good thing, but Facebook is an unweighted graph. Any questions? There is another distinction between graphs that is important to talk about, is whether a graph is simple or non-simple. I'll claim that there's certain kinds of pathological edges. Pathological, let's say, means different, okay? Like, for example, a self-loop. If we look at that edge, if I have an edge from me to me, that is a self-loop. Can I be my own friend? Okay. Well, depending upon what you talk about, maybe it makes sense, maybe it doesn't. Okay. I guess for Facebook probably won't let you friend yourself. Okay. But some people are their own friend and some people aren't their own friend. Okay. Another thing that we usually assume is that in a simple graph, there is only one edge between any pair of vertices. But sometimes we might have multiple edges between the same vertices. Why might that happen? Can anybody think of a situation? What would it mean to have a multi-edge like this in a social network?
What if there's like more than one way to get from point A to point B?
There's more than one way to get from point A to point B. That would be a multi-edge. In a, you know, what you call it? Maybe some of you guys know each other because you went to the same high school. And some of you guys now know each other because you both took 373, right? So if you, maybe it could be that the source of the friendship or where you know each from is a natural cause of the edge. If an edge was a friendship or a connection, maybe it makes sense to have multiple edges. Okay. Notice in one of my earlier examples, it actually did make sense to have multiple edges between things. Remember back to my circuit example? if the red things were vertices, okay, then notice that both this resistor and this capacitor are both edges from 3 to 4, okay? So sometimes you care about having multiple edges, sometimes you don't. And if you don't have loops and multi-edges, your graph is simple. If you have either loops or multi-edges, we say it is non-simple. Simple graphs are simpler to deal with, okay? We like our graph to be simple because it makes certain algorithms easier, but you need to know whether that's true for your particular application. Any questions about simplicity? Would a directed graph with no self-loops be simple? Okay, well, again, you're allowed there's no reason why, if I have a graph like this, a directed graph. Here's a directed graph. This is simple. If I had two edges like that, it would no longer be simple. If I had a self-loop from me to myself, it would not be simple. Okay? And if I had another edge going the other way, if I view this as two directed edges, this is not simple. Any questions? Okay, good. Another distinction between networks is whether they are sparse or they are dense. Okay? A graph is sparse if only a small fraction of the possible edges, okay, are defined between them. Notice that if you have n vertices, if I have a graph on n vertices, I'll number them 1 to n, what's the most edges I can have in a simple, graph on n vertices? Does anybody know what's the most edges I could have on this? Okay, if I have n vertices, what's the most edges I have? I'm seeing n factorial. N factorial is a big number. Okay, I'm seeing that vertex 1 can be connected to n minus 1 other ones. Does everybody see that? And vertex 2 can be connected to, if it's going to be simple, n minus 1 other ones. I have each of n vertices can be connected to n minus 1 other vertices. And note that I've counted each edge twice. Notice if I have an edge from 2 to 4, I counted it in 2 and I counted it in 4. So this is the maximum number of edges that I can have. Something that's basically like n choose 2, okay? Basically n squared over 2. What is the fewest number of edges I can have in a graph on n vertices? What is the fewest number of edges I can have?
N minus 1.
Well, if I want it to be connected, I need at least n minus 1. But if I don't, not all graphs are connected. So I could, it could be 0, okay? If you can imagine the social network of the hermit society. The hermits of society are people who have no friends. These people, if their Facebook page, it'd be a bunch of these people and none of them would have edges to anybody else. That's no problem, okay? It tells us something about them. In general, though, we say that a graph is dense if it's got theta of n squared edges is dense. And generally, if it has theta of n edges, a linear number of edges, that's typically what we mean by sparse. Social networks, are they going to be sparse or dense? In the Facebook or Instagram world, is that a sparse or a dense graph?
I think
about it.
sparse because if you're a single person, you probably don't have connections to everyone on the social network.
Yes, again, Mark Zuckerberg has, 3 billion people on his Facebook or something like that, okay? But in general, how many friends can you have? Most people, I certainly don't think I have 100 friends, okay? Certainly not close friends, okay? There's a limit to how many people anyone can know, okay? Sociologically, I think that in the world, people have something like an average of 150 friends or something like that, depending if they allow, So generally, you can't be connected to too many people. If the average person has 150 friends, and there are n people in the world, how many edges are there in the Facebook graph? Something like 150n, which is theta of n, okay? So certain graphs are inherently sparse. Facebook graphs are going to be sparse. Does everybody see that? What about road networks? Are road networks going to be sparse or dense? Well, suppose we have a junction, a road junction, and that's going to be the vertices. How many roads can meet in the same junction? If you have a street light, it's 4, right? If you have a crazy intersection, maybe it'd be 5. Some people have seen 5-way junctions. If you go to the course webpage, I will show you. People have over the years sent me the craziest junctions they could find. Somewhere there are, depending upon how you define it, 10-way junctions. You could imagine a horrible world. Okay? But you can't have 100-way junctions just because of the way the earth works, right? You've got to have cars meeting a physical junction. Road networks are sparse. The number of roads grows linearly in the number of junctions. Okay? So most graphs in the world that we deal with are sparse. Any questions? Okay. There's some other things that we talk about, and these are important distinctions, but I would like to make sure we get ready for the daily net problem. I'd like to skip ahead to, to the stuff on, on data structures for representing graphs. Okay? So I'm going to claim that we can represent graphs using 2 different types of data structures. One of which is probably the easiest for you to think about, but generally isn't what we use. These are adjacency matrices. One way we could represent a graph is to set up an n by n matrix, where n is the number of vertices. And if if ij is an edge in the graph, we set the ijth bit to be 1. If there is no edge from I to j, like there's no edge from 1 to 1, we set it to be 0. So we set things to be 0. Element ij is 0 if there is no edge between them. Element ij is 1 if there is an edge between them. Okay? This would represent a network on n vertices and m edges. I usually will use that a lot. N vertices and m edges. Okay? By an n by n matrix. Okay? If I have a n by n matrix representing a graph on n vertices and m edges, how many ones will there be in that matrix? We agree that there's a total of n squared elements. If I have a graph on n vertices and m edges, how many of those elements will be 1 if I use an adjacency matrix?
Approximately 2m.
Well, if it's undirected, it would be 2m, because I would have to have, if it's an undirected graph, if I have an edge ij, that really means I've also got ji in my thing. Okay? If it's a directed graph on m edges, then there's only going to be m1s. If it's undirected, there'll be 2 m1s. Any questions about that? Do people see how you can represent a graph by an adjacency matrix? Okay, good. Now, a more space-efficient way of storing graphs that are sparse, which is almost all the interesting graphs in the world are sparse, is an adjacency list. And in general, for all of our problems, almost all of our problems, we're going to use an adjacency list data structure. How will we represent our graph? If we have an n-vertex graph, we will have an array, okay, of size n of linked lists. Each edge is going to be represented by an element in the linked list. What are the neighbors of vertex 1? Well, there is an edge 1, 2, and an edge 1, 5. Does everybody see we can represent this edge and this edge by basically saying that its element I is if we have the ith list, if there is a element j in ith list, that means that there is an edge from I to j. What is the list associated with vertex 2? Vertex 2 goes to vertex 1. It goes to vertex 5. It goes to vertex 4 and to vertex 3. 1, 5, 4, 3. Okay? Does everybody kind of get this idea? I claim we can represent every graph by an array of n linked lists. Okay? How many elements will the linked lists have? If I have n vertices and m edges, how many elements will be on my linked list? Okay, if I have a graph with n vertices and m edges, what is the size of my total size of my linked lists? I'm seeing n times m, and the answer is no. Okay? If I have a particular edge, ij, 1, 2, how many lists is that edge going to be on? Let's think about it. For the edge 1, 2, how many lists is that going to be on? Somebody. 2, right? What list is it going to be on? It's going to be on the list for 1 and the list for 2. What about the edge 3, 4? How many lists will it be on? Okay, it will be on 2 lists. Which list will it be on? The lists associated with vertex 3 and vertex 4. Does everybody kind of see that? So now, what is the space complexity? How much is the total size of these linked lists if I have n vertices and m edges? Starting to see order n, not order n. N is the number of vertices. Okay? If the graph was a complete graph, the total number of edges would be n squared. Okay? I claim the space of this thing is going to be, if it's undirected, it's going to be 2m elements on the linked lists, right? Every edge appears once on 2 lists. Over the entire graph, how many edges will there be? If there's m edges, there will be a total of 2 times m entries on these linked lists. So the exciting thing here is that if I give you a graph that has n vertices and it's a terrible color. So I have n vertices and m edges, okay? The total space should be n for that array plus a total of 2 times m linked list nodes to sum up over all the linked lists. So the total space is going to be n plus 2m, or the space is going to be theta of n plus m. Okay? If I have a sparse graph, this is going to be n plus n. For a sparse graph, this is going to be theta of n. If I have a dense graph, this is going to be theta of n squared. Okay? But if I have a sparse graph, this is going to take basically space proportional to the number of vertices plus edges. Any questions about that? Okay. What if a vertex appears in 3 lists? Well, a vertex can appear in many, many lists, but we're counting the number of edges, right? A way to think about it is, what does a number mean? That's a good point. What does a number mean in an adjacency list? What does that 2 mean? That 2 means the number, the edge 1, 2. Because a 2 appears in the list in position 1, that means an edge from 1 to 2, right? What does this 1 in the second list mean? It means that there is an edge from 2 to 1. Each edge, if it's an undirected graph, each edge will appear in 2 lists. Okay? If it's a directed graph, each edge will only appear in 1 list. Does everybody see that it's perfectly fine if I have a vertex 1 that's connected to all vertices from 2 to n? Yes, 1 is going to appear on every single list. Okay? Except 1's list. There's going to be n minus 1 elements on 1's list, and 1 is going to be in each of the n minus 1 lists, because each edge is going to appear on 2 lists. Any questions about that? This is kind of important.
Professor, is it okay if we go over this slide again? I don't think I understand.
Okay, can we go over this again? What I'm going to do is the following. We're running a little low on time. Well, let's just, what I think I want to do to show you this. Okay, I'm going to take an extra couple minutes if I need to. Okay. Look at this representation and make sure you understand how I'm representing it. I have 5 vertices. That is why I am representing this as an array of 1, 2, 3, 4, 5. Does everybody see how I've got this array of 5? Pointers to linked list because I have 5 vertices, n equals 5. Now, how am I representing the edges? The edges associated with vertex 4. How are they represented? Well, on vertex 4, I have an entry 5. The 5 on the 4th list means there is an edge from 4 to 5. Does everybody see that? The 2 on the 4th list means there's an edge from 4 to 2. The 3 on the 4th list means there is an edge from 4 to 3. We also know that there is an edge from 5 to 4. How is that represented? That was represented by the 4 in the 5th list. that was represented from 4 to 3 by the 4 in the third list. And the edge from 2 to 4, that was represented by the 4 in the third list, right? So one way to think about it is every vertex, okay, is going to have a linked list that's equal to its degree, the number of edges linking to that vertex. If vertex I has a degree 3, its linked list is going to contain 3 elements. But if I go to 3 vertices, if it's an undirected graph, there are 3 vertices that go to me, and those are represented by me appearing in their lists. Any questions of how the adjacency list works? Okay. It is twice, the number of entries is twice the number of edges. Okay, in this case, how many edges are there? 1, 2, 3, 4, 5, 6, 7. I think that there's going to be a total of 14 entries in this list. Let's check it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. See where that number comes from? If you understand how, you have to understand how an adjacency list represents the graph, because that is a critical thing. Any questions? We're going to eat and drink adjacency lists for the next 3 weeks. Okay? So it's important that people kind of figure that out. Any questions?
Just really quickly, is the last sentence on this slide basically saying we can use a doubly linked list to make deletions easier?
What it's saying here, this is something I didn't really need to talk about. Occasionally, to make deleting edges easier, you'll notice that each edge is going to appear in there twice. Okay? So suppose we wanted to delete the edge 4, 5. How do we delete the edge 4, 5 from the graph? Well, we've got to blow from 5th list, we got to blow the 4 away. And from the 4 list, we got to blow the 5 away. Does everybody agree? If we wanted to delete this guy, those 2 entries have to go. And if we want to be able to delete them quickly, sometimes we'd like to have pointers between these 2 copies. Okay, that's kind of what this is saying. But let's not worry about that now. I'm not going to really need that. Okay, any questions? But you see that it is actually worth seeing that to delete this guy, I've got to really means deleting those 2 list entries. Any questions?
Yeah, I see how that's different from what I said. Thank you.
Okay, good. Bingo. So what is the difference between adjacency lists and adjacency matrices? Well, which is better? Suppose I want to test whether edge ij exists in the graph. Suppose I want to know, is Rohit a friend of Brian? Okay. How much time would that take? In an adjacency, or let's make this less personal. How do I know if edge xy exists in the graph? In an adjacency matrix, I would do what? Look up the x comma y element. That would take time, constant time. Does everybody agree? How will I tell, what do I have to do to tell whether edge xy exists in an adjacency list? How do I do it? Somebody tell me how I do it.
You have to go to that list for that vertex and scan linearly.
I go to the x adjacent list, which took me constant time because I'm just going in an array, the xth element. And then I bop through this list until I find y. If I find y on the x list, edge xy is an edge. If I don't find it, I don't. What is the time that that takes? That would take time proportional to the degree of x. Does everybody see that? And that could be large, not constant. So if I really need to check all the time whether two people are friends, a matrix is a good thing. How about if I want to figure out what the degree of a vertex is? Is it order degree? The answer is yes. Often I will say something is order D, where D is the degree of a graph. Okay? What would, which is faster? How would I find what the degree of a vertex is? Suppose I want to know what is the degree of vertex X. How would I find that in an adjacency list? What would I do? How would I find the degree of a vertex in an adjacency list? What do I got to do? Come back here. What is the degree of vertex 4? Vertex 2? Does anybody want to tell me? 4. Why is it 4?
You just count the number of elements, children. You just
Basically, I go bop, 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 bop. The number of things till I hit a nil pointer is the degree. So to find the degree of a vertex in an adjacency list, this should be order D, the degree. How would I find the degree of a vertex in an adjacency matrix? Suppose I have a vertex here, X, and I want to find its degree. How do I find its degree in an adjacency matrix?
You count the number of ones in the row.
How do I count how many ones there are? I go 4i goes from 1 to n. Are you a 1? If so, I bop my count. If it's a 0, no. If it's a 1, bop my count. Bop my count. Bop my count. Don't bop my count. Does everybody see that in an adjacency matrix, it would be order n to find the degree? So if I want to find the degree of a vertex, it's faster on a list. Any questions? Which uses less memory? Well, if I have an n, my adjacency lists take n plus m space. My, my adjacency matrix took n squared. If I have a sparse graph, n plus m is wildly better than n squared. Let's think about Mark Zuckerberg and his Facebook graph. He's got 3 billion people in his Facebook graph. Does he represent this by a 3 billion by 3 billion array? 3 billion times 3 billion is more memory than even Mark Zuckerberg can afford, right? But can he represent it as an array of size 3 billion and then have edges on average of 150 nodes per thing? Could he store that? Absolutely right. Even Skinner could probably store that. Okay? If you have a sparse graph, instead of it being n by n, it's n by 150. Okay? And that was much better. If the graph was dense, really was dense, then matrices are slightly better than linked lists, because if everything's connected to everything else, you have the space for pointers. Okay? But generally, we're going to be dealing with sparse graphs. Which is faster to insert or delete an edge? Generally, on matrices, inserting or deleting an edge is just diddling a bit. Okay? Deleting an edge, okay, from an adjacency list means finding where did we put those two copies, which is basically proportional to the degree of the nodes. Okay? Which is faster to walk over the entire graph? Well, if I have an adjacency matrix, the only way I can walk over the entire graph is by zoop, 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 looking at all n squared elements. If, on the other hand, I have an adjacency list, okay, I can walk over it by just walking over all n lists. this should be n plus 2m steps, okay? So doing an operation on a sparse graph, much faster with an adjacency list. Not just that it uses less memory, okay? But it uses less of everything. Which is better for almost all the problems we will see in life? The answer is adjacency lists. Okay, I have run a little bit long, and what I'm going to do is stop here. But I want you guys to do a little looking ahead before next class, because the daily problem is going to be about using adjacency lists and adjacency matrices. I encourage you to look at the code, ideally in the book, okay, or perhaps the notes, just to make sure you see how to really implement these things, okay? And we will talk about this a little bit more next class. Any questions about adjacency matrices or adjacency lists? Okay, any questions about anything else? If not, yes.
On the previous slide, can you explain the plus 2n?
Plus 2n.
So it was n plus 2n.
How much, if it's an undirected graph, how much is the total weight of the total length of all these lists? As I showed you, here there were a total of m equals 7 edges. And when I look at this thing, you should convince yourself you have 2m equals 14 entries on these lists. Because every edge is represented by a number on one number on two lists. Edge ij is represented by a j on i's list and an I on j's list. Thus, the total length of all those edges is 2m, plus I've got an array of linked list pointers. So I can find the ith list very quickly. Okay? That's why the total space here is n plus 2m. Any questions?
Could you repeat one more time what you said we should do to prepare for next lecture?
Well, you prepare by doing the daily problem, which is going to ask you to do some simple graph algorithm on adjacency lists and matrices. It might be a good idea to look at some of the code I did about how you manipulate edges and matrices, adjacency lists and adjacency lists, just to nail down how that works. Okay,
and that's in the textbook?
In the textbook, ideally. I think that's a great place. If you're too lazy for the textbook, you can look at the notes. But I think the textbook's better.
No worries. Thank you.
Okay, any questions? If not, thanks for your attention. I will see you people in next class. Boom.